So thank you everyone for attending this talk. This is my first time at Black Hat Europe. I think it's your first time as well.
Yep.
So we're quite excited about the whole event. So far it's been awesome. This talk is tackling privilege escalations with offense and defense. So basically I'm going to be covering, well, we're going to be covering a certain vulnerability type in JavaScript engines, specifically in the Acrobat JavaScript engine. It's JavaScript API restrictions bypasses, which allows us to basically escalate privileges. So quick introduction, my name is Abdul. Basically, I manage the analyst team in ZDI. Have you guys heard of the ZDI before? Zero Day Initiative? All right. So basically, ZDI is a bounty program, which is part of the Trend Micro company. And basically, we acquire research from external researchers. And we offer money if they're exploitable or not. So my job is to manage the analyst team, who they basically do the root cause analysis on these vulnerabilities. And I basically make sure that the caseload is being distributed fine in a nice way. Cases are being, offers are being sent, and all that kind of stuff. This is basically myself. Edgar?
Yeah, I'm Edgar Peck. I'm security researcher at Adobe. And yeah, I was on the receiving end of many of the vulnerabilities that actually Abdul submitted. And yeah, so my role is related to security automation, and I'm part of the incidents response team.
He used to fix our bugs, so.
Kind of.
Yeah. Probably we're the most hated people in Adobe, right?
Almost.
All right, so an overview. So do we have any Adobe Reader or Acrobat users here? Of course, awesome. All right, so are we going to assume that everyone else uses Foxit? No? Yes? I personally use Acrobat in a VM, of course. Yeah. All right, so basically Acrobat is an old software. It dates back to 1993. It's probably one of the most, well, according to the poll here, one of the most used PDF readers out there. It's supported by almost all platforms. It's specifically an interesting target for researchers because of the old code base that it has. Plus, it has a huge attack surface, which we're gonna talk about a little bit. So here's my rough architecture, which is Edgar approved, Adobe approved.
Kind of.
Kind of. So I broke it down to 3 components. The main component is the core one, which is acrobat.dll or acrord32.dll. And when you launch the application, basically that DLL is it automatically loaded, and it handles mostly everything. Then you have something called the plugins, and basically Acrobat supports plugins, and these are DLL files, but with an API file extension. There are different plugins. It depends on the type of functionalities that you want, so they're divided. For example, eScript handles all the JavaScript code inside a PDF. So if you have a PDF file with a JavaScript embedded inside it, so basically all that is handled inside eScript. You have other plugins, but it's all based on what you guys want to do. For example, HTML to PDF converts HTML files to PDF files. This is only for Acrobat, which is the paid version of Reader, which is the pro version. XPS to PDF converts XPS to PDF files, and this one has been killed recently.
Yes.
Right?
Yeah.
Because of the sheer amount of vulnerabilities inside this plugin. Annotates handles annotations. Acroform handles XFA forms. And one of the most important plugins is image conversion, and that handles converting image files to PDF files, and that's only supported in Acrobat. So let's not mix up image parsing inside PDF with converting image files to PDF files. So this is 2 different things. If you have an image file inside a PDF file, then it's parsed in a different way than basically converting an image file to a PDF file, which is specifically handled in image conversion in this case. And you have the back-end DLL files that actually does the real job of parsing and all that kind of stuff. I will talk a little bit about some of these DLLs. AXSLE handles XSLT parsing. Interestingly, AXSLE is based on Sablotron, which is an old open source project, which is abandoned. You guys can find it online. You can audit it, find vulnerabilities, and most likely it's going to apply to Acrobat. CoolType handles font parsing. JPEG 2K lib handles JPEG 2000 image parsing. I will also mention WebKit AG, which converts HTML files to PDF files, and it's based on an old spin of WebKit, surprisingly. Onyx32 handles index files. So Acrobat contains a solution that basically create index files for fast searching purposes. And all that is handled inside Onyx32. It got killed as well because of the sheer amount of vulnerabilities inside it. Not technically killed, you can still enable it through the registry, but there is an Onyx32 DLL sitting in your Acrobat reader installation that still contains bugs technically. So how does it look like from a ZDI perspective? So the whole story dates back to the end, December 2014, early 2015, which I personally call the IE rush, which back then we used to receive a lot of vulnerabilities in IE, specifically use after tree vulnerabilities. We were not getting any vulnerabilities in Acrobat or Reader. So we were like, well, let's run an internal audit on this thing, see how strong it is. And because we had a lot of expertise in JavaScript fuzzing, specifically in fuzzing MS HTML inside IE, so we wanted to apply the same concepts of fuzzing, finding vulnerabilities in JavaScript in Acrobat, which we did. And we targeted the Acrobat JavaScript engine. We ended up finding memory corruption, a lot of memory corruption bugs. And by memory corruption, I mean use after freeze, type confusions, out-of-bound reads, writes, every freaking bug type that you can imagine. So we sent the first batch of vulnerabilities back, and that was patched in 2015, early 2015, and ever since things just blossomed from there. So apparently it got a lot of attention. Researchers starting auditing Acrobat, and it basically started we basically started getting an increase in vulnerabilities year by year. And as you guys can see in the past 4 years, it's in a steady increase. In 2019 and this year, it got a little bit slower. And specifically because Adobe started rolling a little bit more mitigations, killing more features like XPS to PDF, which was a huge thing. Which I'll give and also, to you guys.
Yeah. Second part of the talk too.
Yeah. All right. So I'll talk about the JavaScript attack surface. I'll go back a little bit to the architecture. So the key takeaway from this slide is that through eScript, which handles all the JavaScript, you can actually touch almost all the DLLs and force the parsing of a lot of images, image files, XSLT, and all that kind of stuff. I will actually note that you can still trigger parsing of WebKit AG, but it still requires an API restrictions bypass. So technically, you can touch everything in the backend through eScript. So this is the key takeaway here. And this is very important from an attacker's perspective, because if you can trigger an image parsing through JavaScript, let's say you found a heap overflow in JPEG 2000, which happened in the past, and you can trigger the parsing through JavaScript. So basically, you can do your own heap spraying, crafting in a nice way, trigger that parsing, and exploit that vulnerability, so which is awesome, right? If you control everything through JavaScript, from an attacker's perspective, it's a win, right? So let's talk a little bit about the engine itself. So the engine itself is based off SpiderMonkey. It's a spin of an old SpiderMonkey version, 1.8 specifically. It exposes a rich set of APIs, for automation purposes, annotations, collaboration, manipulating forms, and all that kind of stuff. A lot of the APIs that exist in Acrobat are not exposed in Reader, the free version. There's a lot of mitigations. Well, not a lot of mitigations. Some mitigations, apply to the JavaScript APIs, specifically separation, privilege separation, which we're going to talk a little bit about after. I will also note that Adobe has been doing, a good job in enrolling more mitigations. For example, they compiled, all the plugins with CFG now, but you still have some things missing.
Areas for improvement.
Yes, well, there's progress, which is awesome. And the last thing that I want to mention about JavaScript APIs is that they're executed into 2 contexts, and this is actually the core of this talk. You have privileged context and non-privileged context. So what are privileged and non-privileged contexts? So if you go to the JavaScript API reference that Adobe has online, you're going to notice that some APIs have a red S next to them, and some APIs do not have a red S next to them. So the ones that have that S next to them, it means that you can only execute these APIs from batch console or some privilege event. You cannot actually do it from the normal doc event. By doc event, I mean when you open the doc, a document, a PDF document inside the application, it basically runs in a doc privilege. And you cannot execute these privilege APIs from the doc, right? So you actually need a way to do it. And if you try to actually execute a privilege API from a doc context, then you're basically going to have a security warning. And this is an example of executing launch URL, app.launch URL, from the normal doc context. And basically, because you don't have privileges to execute that, it's going to give you that warning. Like, do you want to accept it or not? That said, you can still execute privileged APIs from non-privileged context. And that's by something called trusted functions, which was introduced back in version 7, in Acrobat version 7. And the whole idea is, if you want to execute a privilege API, it has to be a trusted function wrapped in a begin priv, end priv block. And to define that, you have to define that through the app.trusted function. Though there's a caveat here. Trusted functions can basically only be executed from trusted locations. So you cannot just embed them inside a doc. And that's where the folder level scripts come in play. And that's a concept that was introduced by Adobe as well. So they have specific folders that are trusted where you can put your scripts in them. If they have trusted functions with privileged APIs inside them, then you can execute them from non-privileged context. By default, there's one directory that comes in Adobe that's actually trusted. And if you check your Adobe installation, there's a directory inside it called JavaScripts. And if you dump any script inside that, then basically you can execute privileged APIs. There is one file inside that directory that comes by default. It's a bin file. And basically that bin file is a compiled SpiderMonkey bytecode. One thing I want to mention here is that I mentioned that there's a doc context where your document gets executed. And also there's something else, which is the root context. Think of it as root, which is the higher level, and there's doc, which is the normal user level. Okay? Usually when folder level scripts gets loaded, they get loaded in a root context, not in the doc context. Right? But the doc can still call these functions from normal context. Anyway, so to decompile this bin file, there's a researcher called Molnar who actually, basically spoke about the whole privileged unprivileged thing back in early 2014, and he released a tool that allows us to decompile the bin file. And if you run the tool, basically you're going to end up with a huge JavaScript file, 27,000 lines of JavaScript files. Basically, it's not the best output. If you modify the tool a little bit, which Jazel Spellman, one of the guys on our team, basically he modified the tool so it basically dumps the comments as well, which is awesome. Because in that JavaScript code, there are comments that reference bugs and stuff like that, which is quite awesome. So once you decompile the code, you're going to end up with that nice JavaScript that contains a lot of trusted functions that we can actually start calling and analyzing and auditing. All right, now to the fun part, which is basically attacking the engine. So first of all, why am I talking about all this? Why do we want to bypass restrictions, right? There's a couple of points here. The first thing is that it's very possible that we can actually use privileged APIs to gain code execution through pure logic chain. Forget about memory corruptions and all that kind of stuff. And it has been proven right. Back in 2015, we actually found a bunch of undocumented APIs in Acrobat that did a whole bunch of input-output things on disk. Let's say it allows us to write files, delete files, create folders. And when we found these undocumented APIs, we were pretty shocked. But they were privileged. So we needed an API privilege bypass in order to execute these specific functions. And basically, we used all that, chained all that together, and we were able to get code execution through just a logic chain, which was awesome. The second thing is that we might be able to trigger more interesting functionalities. Let's say leak files through these privilege APIs. I mean, do a bunch of other stuff. And most importantly, and from what we've been seeing in the CDI, most of the non-privileged APIs have been heavily audited, due to fuzzing efforts and stuff like that. We've been seeing a lot of, recently a lot of image parsing vulnerabilities, which is awesome. Don't get me wrong. Image parsing is sweet, especially if you can actually trigger it from JavaScript. But it's still better if you have a JavaScript API bug, right? That said, we came up with a conclusion that the privileged APIs have not been audited heavily. They have not been touched. They have not been touched to a point where back in 2016, I found a command injection in one of these, privileged APIs. So that's how weak they are, right? Of course, it only affected Mac installations of Acrobat. It didn't affect all the installations, but it's still a command injection and an API, a JavaScript API, which is huge. So that's basically it. That's the reasons why we should definitely do that. So let's talk about discovery. I broke it down into multiple steps. So I mentioned you have root context, which is the system level context. So the first step is to actually achieve a system level eval. And by system level eval is literally just placing your code from doc inside a function in the root context, which is the folder level script, and get that executed. Once you get that executed, then it's going to execute in root context. This is the first step. And this is basically just a universal way. You can use that all over the place. The second step is to find all the trusted functions inside the folder level script. And that trusted function must have a begin priv and end priv block. And the last step is basically, not the last step. Inside the begin and priv, we have to find something that we can overwrite. And basically, if we can overwrite that, we can overwrite it with a privilege API. And then we can get privilege escalation, or execute that method. So let's talk about the first step, which is basically acquiring a system level or a root level eval. So this function, af parse date, is a decompiled function which is found inside the bin file. And since this actually runs in root, if you notice, you have the long entry argument over there, and all the way down where the arrow is, you have an eval that basically takes an argument, which is long entry char at. And because we control the long entry argument, so then we can actually forge that argument and basically have char at point to our own JavaScript function. So now we actually have a JavaScript function executing in root context. That's the first step. So now let's talk about the escalation. And as I mentioned, we have to find a function in that folder level script that's trusted and that has a begin and end priv block. And that's the first bug that we actually found, which is 2015-3073. It's a very simple bug. Remember, the engine back then, it was very weak to a point where it allowed us to actually overwrite system objects. Technically, we should not be overwriting collab because it's a system object. But that bug basically allowed us to overwrite that specific object. So that said, if we look at the function, it's a trusted function. It has a begin priv and an end priv block, and inside it, it has a call to isDocCenter URL. All we have to do now, since we're in root context, is to create our own collab object with a custom isDocCenter URL, basically have it point to a privilege API, and then get code execution, right? Not code execution, well, privilege escalation. So this is how it looks like, chaining it all together. The first part is basically execute a JavaScript function in root context, which is using af parse date. Of course, the exploit code is just a function that overwrites, isDocCenter URL with our custom privilege API. In this case, it's app.launch URL, which is a privilege API, just for POC contact, just as a POC. And then escalate, which technically executes app launch URL from inside the begin priv and end priv block. It's as simple as that. So the fix. I mentioned that, we can overwrite collab. We can overwrite app, right? If you see here, I basically overwrote collab with app. and basically collab now is app. So the fix was super simple. Do not allow that thing to happen. Just these are not writable objects. So it was a simple fix. Did it work? It did. It actually did. So basically, we were not able to escalate that way, but they still left other objects writable. And one of the objects is identity, which is still writable, by the way. So identity basically contains all the information of the current user who's using that application. It contains his username, his login name, his email. And if we run a search for identity in the folder level script, we will notice that it's used all over the freaking place. And in this case, it basically references the email property out of identity. So we figured out that, well, if we create a getter for that and execute our own privileged API from inside that getter, then basically we bypass it. And that's exactly what we did. And it was a simple exploit, simple bypass. So the way they fixed it, I personally thought that would actually, restrict overriding that object. But what they did is they denied executing privileged APIs from inside getters, which is very good because in that case, they would mitigate a whole bunch of other similar scenarios inside that folder level script. Sorry. So how did we bypass that? So I personally thought, well, okay, since Adobe is actually doing a good job in securing mostly everything inside the folder level script, let me think a little bit outside of the box and target other objects. And basically, I ran through the global object. And the global object is very, very interesting because it allows us to create variables and to share those variables among different contexts. So let's say I want to create a variable in a doc, but I want to use that same variable in another doc. You can do that with global. And you can go even further with global, that you can actually save those variables on disk. The only caveat here is that it only saves those variables on disk once you close the application. So first, you create a variable, and then you call an API called setPersistent, and then it's going to flag it as, well, save it when you close the application. Once you close the application, then it writes it on disk. And then once you launch the application again, you can still use those global variables. So it's a nice concept. I think they killed this in early 2019.
That's
right?
correct.
Because it's a, yeah. So the whole idea is basically to create a variable, create a getter for it, and launch a privileged API from inside the getter. Specifically, this works because in the saving process, it actually when it's doing the saving, it's doing it in a high privilege already. So this was, it worked flawlessly, but it only worked when you're closing the application. So basically, you can trigger the escalation once you close it because it's actually saving it. That said, they fixed it, basically. They denied doing that as well, and now they killed the whole global, save to file kind of thing. And then after that, in 2016, we received, well, at the ZDI, we stopped doing research in, privileged APIs, and we decided to keep that apart. So we started receiving submissions from external researchers, and we received an interesting one from Matthias Kaiser. Now he works for Apple. He's a sharp guy. He knows a lot of JavaScript and Java. So he approached the problem from a totally different perspective, which is through proxies. So he scanned the folder level script, and he found out that there's this thing, API called xqdialogue, that's used all over the place. And basically, it allows you to load dialogues in the application. And it's always used in a trusted function in a begin and priv block. So basically, this is ideal. So what he did, he basically grabbed a reference to xqdialogue and had it call his own handler, kind of like setting a trap for it. And his handler basically just was able to call a privileged API, and he was able to get escalation out of it. Adobe patched this in an interesting way. They basically denied having reference to any of these APIs. So now if you try to get a reference to app.xqdialogue in order to have a trap for it or something, then you're not going to be able to do so, which was quite interesting. That said, we left the whole topic. It went idle for a little bit of time until last year. I heard rumors that there are some JJS API bypasses out there, so I decided to have a look at it again. Apparently, they did harden a lot. Adobe did a lot of good job, a good job in hardening, JavaScript bypasses and stuff like that. We cannot overwrite objects. We cannot do getters. We cannot do global. So I was like, OK, so let me see what I can do. So I was like, I didn't have a look at objects inside objects. So let me look at that. So I wrote a small script that basically iterates through each system object and checks if there are any objects inside each object that are writable. And I found out that there's an object in Collab called drivers. And surprisingly, that object was writable. So I went right ahead to the folder level script, scanned it, see if it's actually being used. Surprisingly, it's being used. And basically, it's calling two functions from inside one element of that object, which is an array. That said, I went ahead and applied the same concept, which is basically, override that collab object with that object with my own custom object, and set the proto to it, because I was at that time executing a privileged API from the actual collab object. So that said, if you want to craft your own fake object, it has to have the same prototype of it. So that's why I set the prototype to collab. In the end, it was patched. They hardened it further. There was also a bug that he's probably going to go over it, which was interesting. It deals with mutable variables. And basically, it allowed us to overwrite read-only variables. And that was a little bit more devastating. But I'll let him talk about that.
Okay. Thank you.
So he's going to go over the, defending the engine.
Yes. So, yeah, Abdul talked about attacking very specific engine in a very specific way. So I'll try to, try to convey two messages. First is how we can defend against the specific thing, but also there is a more general idea about defending JavaScript engines. Because so to step back, the problem is more general than Acrobat. The problem is that JavaScript is used in a specific way. So JavaScript was developed a long time ago, and at the beginning it was, according to, I don't know if it's true or not, developed in 10 days by Brendan Eich, and then it was called Mocha, and it was with the goal to introduce functional programming and allow easier way to write code for web developers. And it took almost 10 years to come to somewhat stable version in 5th edition in 2009, offered some more stability and introduced taming of the language through strict mode. After that, the sailing was a little bit more smoother, and nowadays we have incremental improvements to the language. But it was not clear where it will go, right? And that's good, because it gives developers a lot of freedom, because design decisions is to be easy to learn, and it has a lot of dynamicity. It helps writing the code, but it comes with a price. It comes with the price in analyzing the code and securing the code that is written in this kind of languages.
It's JavaScript. So.
Right. So what are the key features that are hard from securing or analyzing program analysis perspective, right? So the dynamicity, right? The key dynamicity, but before going into detail of that, there is also prototype-based inheritance, which is, I think, somewhat unusual, right? It's not typical class-based inheritance, and when you write code in that fashion and you're not used to it, you might make some assumptions that do not hold, right? And some of the exploits actually reference that, where there were some assumptions that prototype will not be writable, or that already exist, or there is some magic there that happens, but you can overwrite it in a certain way, right? So, and again, the dynamicity happens through multiple ways. There is a way to add or delete prototypes, to do a lot of modifications on the fly. Again, helps developers, does not help securing it. The other thing is generation of dynamic code generation through eval and friends, and also it's not quite statically scoped. It means that static analysis, if you use it essentially fails. So you have to make some assumptions and tricks there that to make it work a certain way. As Abdul talked, I won't dwell on this. So why is JavaScript used at all? Because it extends functionality, essentially, right? And the problem is when you allow the core of the application that has some security critical resources, as Abdul mentioned, access to some image conversion or certain parts that are supposed to be protected, or even a privileged version where there are workflows that assumes that your PDF is trusted and can access a file system. That kind of functionality needs to be protected, right? And essentially, you can think of it in a very abstract way at tool level. So there should be public resources that are accessible to the untrusted API, and there should be security critical resources, and there is well-defined separation of concerns there, right? And how is that usually done? It's usually done with something called reference monitor, and you can think of it as a language-based sandbox, right? And as there are sandbox escapes, in a more standard way, there is a language-based encapsulation escapes, right? Which Abdul mentioned before. And the challenge is how to prevent that reference monitor to leak those references, right? Because if you think about offensive part of the presentation, it was always some way to get access to some references and then kind of pivot from there and access a critical resource, critical reference, right? So this is the key implementation problem, right? In one slide, just you have to ensure that untrusted API does not have some way to get to the critical resource. And how do you do that? Well, you have to somehow confine the API. So ensure that untrusted code does not use public API to access the security critical resources. And in the abstract sense, how can you think about that? So if you can abstract all the bugs that Abdul showed, it would be some variant of this, right? It would be there is some API, public API that reaches a reference R1, for example, and a trusted JavaScript get access to that, and from that you can think of it as some sort of tree of embedded references that lead to certain parts of the program functionality, and then imagine there is a path that goes, through sequence of references to a critical resource, right? This is an abstract view of all of that, right? This is the only when if you are defending something, you have to step back. You cannot possibly go and check every of these things manually, right? And let me just demonstrate this with a simple example, right? Let's say you want to protect this event queue implementation, which is, let's say, some queue implemented via stack, and you have a public API that only pushes, puts the thing onto that queue. And the goal is not to allow the event queue reference to leak. So this is just one function, and it clearly works. It's hope you can convince yourself that there is no way to leak your reference to event queue. However, if you just add one more function, which is this add, which puts theoretically the event or whatever you're using in some location, the things are not so simple anymore. So I don't know if you see how this is problematic, but it is. Right? You can actually leak by adding in JavaScript. There is no rule that the index has to be homogeneous. It can be an integer, it could be a string. So if that string corresponds to the function, then if you invoke the same function, you will that is the way to leak a reference. Right? And that's essentially, this is in short simplified version of all the exploits, right? All the exploits are, much more complex and involved, and they use domain-level information to somehow leak the reference and then do something interesting. Here, I just get handle of the reference. Of course, for the exploit, you need to do much more thing. I'm not saying this is all the story, just the critical part of the story, right? So I was in academia for a long time, so I have bunch of this quotes my mind, and way back in there, I think this is appropriate because we are in England, right? And Sir Hoare said that you can construct software in two ways. One, that it's so simple that there are obviously no mistakes, or so complex there are no obvious deficiencies, right? So ideally we'll go with the first route, but that would be hard, right? That would be hard because JavaScript is hard. So the goal. So this sort of ends the first part of my talk, where I put it in a bigger picture, but now I want to talk about how to analyze these things and how offensive part improve defense through static analysis. So I tried multiple approaches, and there are multiple ways to kind of skin the cat, if you wish, but static analysis is one that kind of worked the best. So for static analysis of JavaScript code, there are some issues to overcome. First, you have to deal with the heap allocation, and then you have to deal with aliasing. Like aliasing in any other programming language enables quick sharing and across the execution, and it's an essential feature. However, it breaks encapsulation, it breaks modularity. And then when you have to think about invariant setup on a global way, logic breaks down, and that's where vulnerabilities creep in, right? Because you don't have this modular, clear view of what is happening, right? But that's because you are trading simplicity of writing for the kind of difficulty of reasoning about code, or having silent assumptions that are not quite fleshed out, and that has to do a little bit with development of the language. So I will talk about static reasoning of security policies in a second. And the key thing here is points to analysis, because points to analysis essentially gives you all this information about how these references are corrected. How do you gain access to all these references, and in which way they talk? Because as Abdul told, there is bypass on the bypass on the bypass, right? Over the bypass. And that's always some bypass of some reference, right? Some reference was there that you think it was not there, and only points to analysis can give you that information. However, it's a very challenging problem. It's deceptively simple. What objects can a variable point to, right? And even if you look at this simple example, for basic points to analysis, I won't go into details because I'm running short of time, but essentially, for example, if you call identity function, you can see that it does not distinguish between allocation of A and B, right? So this is a function constructor for the class, and you are missing certain information, and this would introduce imprecision with a lot of false positives, and it would mean, well, either there are too many bugs that can't all be bugs, or that I'm just missing something, because maybe I can reduce this in some way that is not completely understood or not sound. I will come back to soundness a little bit later. And then you can introduce context sensitivity, which essentially adds a call site. So if ident function is called from a specific call site, then you can add precision, right? But that's my bigger point is points to analysis is complicated problem, right? In 2000, way back in the day, 20 years ago now, it was like, haven't we solved this problem yet? And we haven't. It was around 800 references about points to analysis, and now, since 2001, there's 6,000 more references, papers about the same topic, right? And the problem is hard because there is no, library which you can use, which will give you the information, and you will be able to use that in a simple way and get, well, this points to there, and if I can only make sure there are no paths from from reference that is public to the reference that has security critical resource, then I'm done. It's hard to establish that kind of information. Either you get too much paths and then it's useless, or you just not sound, doesn't give information. And the other difficulty is that's how the paper looks like, by the way. If you go to check one of these papers, they are impenetrable. It's impossible to understand what is going on, right? So I will take a different approach, where instead of giving you an imperative description and re-implementing everything every time Abdul sends us a bug, I have to re-implement kind of scramble, because offense is asymmetric toward defense. Defense always have a harder time. Even the presentation is harder for me. So on the high level, what you need to do is you have to get a program and then syntactically derive two relations in this case, assign, alloc, and assign. That's the input. And then data log rules, as you can see, it's pretty much just a base step. And then this step is essentially the recursion step, which is bottom up. You build the points to relation bottom up. And then this is just the basic idea, basic principle, right? So 30 years ago, this would be an AI talk. It's not AI talk anymore. Data log is not the cutting edge of artificial intelligence anymore, but it's pretty useful in program analysis. So just let me demonstrate how you can improve precision of your analysis, because that's critical. it's critical to improve precision of points to analysis based on the information. In our case, it was from the information provided by Abdul's research, right? Because then you can always improve analysis in a way that you think it will work, but you don't know exactly how. And it's very hard to add precision to JavaScript without adding specific features that are maybe tied to your engine. Right? Maybe you need to specify something that is tied to your engine, right? So even this points to analysis that I am presenting is not one size, but I'm arguing that there is a way to develop points to analysis, for your application potentially, or something that you are using quicker, right? And potentially understand problems upfront. So the kind of higher level, I guess, point, maybe more theoretical academic point is that static analysis is basically combination of mutual recursions. And if you want to implement that iteratively, it becomes super difficult. You have this work lists that you have to flip if you want to do it efficiently, and it becomes super, super hard. So the pragmatic way is to use recently introduced data log analysis. It's University of Athens that has a lot of good research in that area, and they're making good progress there. So let me just show the one rule that would take care of that would detect the vulnerability that Abdul hinted at the end that is too complicated. It would require probably another 25 minutes to talk about, and it's captured in this, in these two rules. So the first rule essentially is reachability. It's essentially path from one point to the other, relating any two heap locations, and mutable access essentially requires to, if you remember, store field was extension for the field sensitivity, and essentially points to information in previously defined reachable information. If you apply that concretely to JavaScript Engine in PDF, it would deal with Colab and app and any other object that you want to secure, right? And it doesn't have to be that. In the browser, it could be some DOM-related object, right? So this is not, this is not tied to the engine. There are some tricks that are tied to the engine, but I don't think I need to talk about them here. So the one other point that I would like to make is that points to analysis is good, but it can get you so far, right? With secure information flow, I might be familiar more with that. The points to analysis can even give you more information. If you lift the level of reasoning from the reasoning between expressions and heaps to capabilities, right? So let me just step back before I continue with this. Initial secure information flow has traditionally been seen as, well, we have some abstract analysis and we use points to information as a client. Right? But that doesn't have to be so. Again, the recent research, and I think it's very useful, some recent academic research that was applied in a real setting is to use it in a way to combine these two concepts. Because when you think about it, flow is essentially points to. The only thing is the domain of reasoning is not the same. And they are not quite the same because transfer of, for example, tatedness is slightly different than transfer of heap points to information, right? But the key idea is to combine those two things and make the analysis powerful, make defense more powerful, and provide more richer rules to check for for parts of the information security of the flow that potentially lead from tainted source to the critical sink, right? So and for example. If we lift this reasoning to talk about privilege escalation of some heap location in general, you could introduce two methods for sensitive sink methods, and then you have to construct a call graph. And so call graph is yet another sub-lecture about JavaScript. It's very hard to construct because it's completely dynamic. There is no static call graph like in C or Java, right? And so again, the rule is very simple. My bigger point is that this is the only way to quickly capture the offensive part, to quickly capture what bugs are coming and how to essentially adjust and leverage static analysis to potentially kill small chunks of bugs quickly, right? And so now let me talk a little bit about why couldn't we do that upfront? Why couldn't we just make this analysis 2014 or 15 and solve all the problems and make JavaScript Engine amazing, right? The thing is that there are three competing directions in static analysis, and ideally you would have both, but that's impossible, right? Let me focus a little bit on soundness. This is soundness in mathematical sense, not in colloquial sense. Soundness that it covers represent all possible programming executions. If you go that route, and in academia that has been the traditional route, you will end up with, you will either kind of lie, or you will just ignore that. You will say, well, I don't know what happens, it catches some bugs, and I'm done, right? And that's the problem, because then you won't catch all the bypasses that Abdul was talking about. So the idea is to be somewhere in the middle, right? To be kind of soundy. To be, because you can't completely model all executions. So you can, but it becomes useless, right? So what is interesting point that again came out of academia is that soundness is not necessary. And I think what I want to argue here is two things. Soundness is not necessary to make static analysis useful, and also you can leverage offensive research to kind of gauge your soundness, right? So soundness is not binary, so it's either sound or not sound. In strict theoretically mathematical sense, that's true, right? But when you talk about pragmatic program analysis, you want to lever or gauge to sort of adjust what you want to do, and I think offensive research offers a lot in that direction. So what are the takeaways? I think. I'm glad that you stayed for the defense part. I think the tech part was awesome, amazing. So what can we take away from this? I think despite the great influx of bugs and great research on the offensive side, it's still possible to catch up to some extent with defense, right? And in sort of a specific way where you want to limit your problem to, if you limit your problems to JavaScript APIs, understand the difficulties of the language semantics, and try to assure confinement, but do it in sort of incremental way. Declarative specification seems to me the only way to go if you want to have kind of a fighting chance against the kind of asymmetric nature of offense part. And then again, just to reiterate what I said at the last, you don't have to have a tool that it will work, that will prove your code correct. For my PhD, I did that, right? But it's super hard. So it's just impossible to prove that the code is correct. So you have to make trade-offs and give up soundness in a certain way, and hopefully measure and adjust it in certain way. And again, I want to emphasize that highly enough. I think Abdul's great research helped a great deal in that sense. So,
from the offensive side, specifically for Acrobat, I think things got a little bit harder. I think it's still possible to bypass API restrictions. There are still a lot of other attack surfaces in Acrobat that we didn't cover. Because they keep adding more things over that application, so it basically exposes more attack surface and more attack surface. So that's it for me. If you guys have any vulnerabilities, please send them over. We're going to pay you for that. Shameless plug, right? But that's it. Any questions?